yesterday we learned some adder concept, right? So what was the adder we learned about yesterday? So carry, skip adder, right? So today we are going to learn a new concept called as carry save adder. Okay. So this carry save adder is very much different than other adders what we have learned previously. Okay. So that's why I didn't explain in yesterday class because it was something like it is used different concept among all the other cadres. Okay, so coming back to the class, before researching about carry save adder. Okay, so we should memorize like what was the adders that we have learned so far, right? So today we are going to learn one of the most important adder, right? So that is used inside the modern processor multipliers, DSP system, and AI accelerators. Okay, so that adder is called as carry save adder. So before learning CSA, let's recall what we have studied previously. We have studied like ripple carry adder, carry look ahead adder, carry select adder, and carry skip adder, right? So can anyone tell what was the main goal of all those adders in the chat? What was the main goal of all the other adders that we have learned so far? Will tell us like what is the main goal of all other adders? Okay, so we learned something called as propagation delay, right? Carry propagation delay in all the others like a ripple carry adder, in carry look ahead adder, carry select adder, and carry skip adder, right? So all these adder we had something called as propagation delay, carry propagation that to carry propagation delay. So what is carry propagation delay? Like the time that is taken to like propagate the carry from one adder to another adder, right? So to reduce these all these things, we implemented like from a ripple carry adder to carry look ahead adder, from carry look ahead adder to carry select adder, and carry select adder to carry skip adder. From like from these type of adders, we went on decreasing the delay, right? Like for example, to go through the concept means like in ripple carry adder, the carry propagation delay was like from it was calculated in first adder, and the delay will be in, went to the second adder, and there it will stop and it will calculate the carry and it will be sent to the next adder, right? Like this how it was working in RCA. So their delay was more. When coming to carry look ahead adder, what was the carry look ahead adder was doing? It was like checking the possibilities, right? So coming to carry select adder, what was this carry select adder was doing? Carry select adder was like it was checking probabilities, like possibilities. It may be zero, it may be one. Like it's dividing into two groups, okay, like upper and lower. So either in either way, upper can receive only zero or one, right? So it's were dividing into two groups. Then based on that, it was going to calculate with both zero and one carry. After that, calculating your original carry, you will go through the what you are going to choose, right? So coming to carry skip adder, it was like it used to skip the carry, right? So if all the propagation group of all the adders is one, then it will directly skip, or else it will run as like RCA, right? So this is what we have learned so far, like what the this carry does. So from adders to adder, we used to reduce a propagation delay, right? From like RCA to CL, carry look ahead adder, carry look ahead adder to carry select adder, and to the skip adder. We went on like reducing the propagation delay, right? So what I'm trying to say is that all those adder have one common limitation. Okay, so the adders that we have learned so far has one common limitation. So what is that limitation? They are designed primarily for adding only two numbers. Okay, so what we are doing, we were adding a and b, right? Input a and input b, like we never did add input c, right? So so the limitation of all the adders that we have learned so far was like we can't add three numbers at a time. So okay, that was the main limitation of all the adders that we have learned so far. Now suppose if I want to add three numbers, okay, 10 numbers or even 32 numbers together, okay, will RCA be efficient? No, right? Because it was primarily meant to add like a and b, right? Like a of 0, b of 0, a of 1, b of 1, right? Like it was how it was working like for RCA, right? So this is why exactly we are using carry save adder. Okay, so carry save adder was exactly used for this purpose only. So before knowing better of CSA, carry save adder, just we will go through a recap of previous adders. Okay, so what was going in RCA? Like carry travels from stage by stage, right? Like one adder to another adder to third adder, third to fourth, like that it was going. Okay, so what was that limitation? Simple slow propagation means delay will be more. Coming to carry look ahead adder, like here parallel carry generation was going. Okay, so the difference between carry ripple carry adder and carry look ahead adder was in carry ripple carry adder propagation delay was more, so that too was reduced inside carry look ahead adder. Like how it was reduced in RCA, it was calculating in series. Coming to CLA, it was calculating carry in parallel, right? So major of that propagation delay was reduced in this formation only. Okay, so coming to carry select adder. So in carry select adder, the delay that was somewhat improved by carry look adder has further been improved by carry select adder. How? By dividing into groups and calculating the carry for both possibilities like zeros and one. We have improved somewhat delay, right? So coming to carry skip adder, uh, here what we are doing further, the skip speed was increased. How it was increased? Like if we used to create a propagation group, right? So based on the propagation group, if every propagate value of every adder is 1, then we will directly skip the carry, right, to the final, right? So that this is how we used to calculate in all other adders. So now, although this adders improves speed, okay, like this CSLA and CSK have improved the speed, all of them still depend on some carry propagation, right? Like still there will be some carry propagation. So and what was the other thing they were doing? They was mainly adding two operands, right? This become problem in multipliers. Okay, so can anyone tell like where we need to add many numbers together? Can anyone guess where we were adding many numbers? Okay, I think none of them did the yesterday's task. So okay, no problem. Okay, listen here. So we are adding many numbers inside multipliers, DSA, DSP processors, MAC units. Okay, so this is where we are adding many numbers. So yesterday I said right to know about why we are using multiplier or multiplexer inside that block diagram, right? So this is what use. Okay, it was going to like adding carry of all other adders. So this is what we used to do inside that. Okay, so why did we introduce carry save adder? So as I said, the all other adders had limitation, like we can't add three numbers at a time, right? So suppose we need to calculate a plus b plus c. Okay, using ordinary adders, what will happen? First we were going to do a plus b, then the answer will be added to c, right? Like this is how we are going to do if we add use our ordinary adder, right? So did you like after hearing this example, did anyone notice like what was going on? So there carry propagation occurs twice. How twice? Like think you're adding a plus b, okay, and after adding a plus b you will get some carry, right? So there it will wait for one time, and after adding c, that result of a plus b adding with c, there you will get another carry, right? So there carry occurs twice, right? In that example, like a plus b plus c. So now imagine you are adding 32 numbers. Okay, now we just added three numbers. Imagine we adding 32 numbers. Okay, so what happens in adding 32 numbers? The carry propagation occurs again and again and again, right? Till you add all 32 numbers together, right? It will carry will be generated in all the steps that you are adding, right? So what happens at that time? Obviously, the delay will become going to huge, right? So it will create more delay. Why? Because each stage the carry you are generating a carry, and it will be like creating a delay. Like what to do with this, what to do with this carry. It was thinking like that, right? Your design. So in multipliers, many partial products are generated. Okay, so example like a 32-bit multiplier can generate 32 partial or products, right? So just think like that. A 32-bit multiplier can generate 32 partial products. So adding them sequentially, like I'm adding one bit multiplier and another bit multiplier, like that. If we are adding means obviously that will be become extremely slow, right? So what I'm trying to explain is that CSA introduced a brilliant idea. Okay, instead of propagating carry immediately, as the name suggests, what is the name of the adder we are learning? Carry save adder, right? It's going to save the carry. Okay, like it will save that carry produced in that operation, and it will tells I will add that later. Okay, so instead of creating a delay, it says that now I'm not going to add that carry. I will store that carry, and after every process, I will lastly I will add that carry. Okay, so this is how your carry save adder is going to think. So this is how the name carry save adder came. Okay, so yeah, so what is carry save adder? we are formally going to define a carry save adder? So carry save adder is nothing but carry save adder is a digital circuit that adds three operands simultaneously and produce two outputs. Okay. So what are the two outputs? The two outputs are sum vector, carry vector. Okay. Just remember these two words. Okay. What is the two words? Carry vector and sum vector. What's then what can we repeat the like what is carry save adder? Carry save adder is a digital circuit that adds three operands simultaneously and produce two outputs. Okay. So what is the thing going on here? We are not propagating carries. Okay. So I need to know one thing. Does using CSA do we find the final answer? Like using this adder, do we find the final answer? If your answer is yes, then it is wrong. Okay. So using carry save adder, we cannot find final answer. Okay. So this is the most important concept of CSA. What like we can't find the final answer using carry save adder. Okay. So what is the main thing of carry save adder? Carry save adder is not going to give the final output. Okay. It's only reducing three numbers into two numbers. Okay. So this is what the carry save adder is doing. It's only going to reduce the numbers. Okay. So just for your better understanding, think CSA as a compressor. Okay. So what the use of compressor? Like it will compress your original data into lesser weight data, right? So like that only carry save adder is going to compress three operands into two operands. Okay. So how this CSA works then? So let us understand how CSA actually works. Okay. So suppose we have three numbers A, B, and C. Okay. So every bit position get one full adder. Okay. Like think your A, B, C have n number of bits. Okay. Like just think of 4 bits, 4 bits, 4 bits. Okay. So what is the meaning of every bit add handled independently by one full adder means this is nothing but A of 0, B of 0, C of 0 is going to handled by one adder, and A of 1, B of 1, C of 1 will be handled by another adder. So this is the meaning of like every bit will be handled independently by one full adder. Okay. See here like this A0, B0, C0 will be handled by FA0, and A1, B1, C1 will be FA1, and like this it's going to work. Okay. So that every full adder, that one full first full adder like which is handling A0, B0, 1 C0 will going to generate two bits. One is sum bit and another is carry bit. Okay. So that is what we formally understand about carry save adder, right? It was going to generate two bits. Okay. What is that? Some bit and carry bit. Okay. So before thinking that, what we were doing inside a RCA, ripple carry adder, in our inside RCA, the carry was going to next full adder, right? Like FA0 to FA1, FA1 to FA2, FA2 to FA3. So But inside CSA, carry never goes to the next full adder. Okay, like for FA10 to FA1, it will never goes. It will be stored. Okay, it will be stored in some place. So what happens if it stores means, if it the carry is stored means it will completely remove the chain, right? Like it never goes to the FA1, FA2, like that. It will never travels, right? So it's removing the chain. Okay. So just look at this architecture. Okay, there is a 4-bit CSA, a 4-bit CSA. Okay, 4 bits nothing but, okay, every bit has, every input has 4 bits, right? Like A0, A1, A2, A3. How many bits? 4 bits, right? That is why, like if input has 4 bits, then it's called as 4-bit CSS structure. 8 bits, 8 bit. Like that, we are going to define 4-bit CSS structure. Just look here. For 4-bit CSA, how many full adders we have? 1, 2, 3, 4. Why? Because for one set of bits, we have one full adder, right? Like A3, B3, C3, one full adder. A2, B2, C2, one full adder. Like how this is we are using, right? So what is the thing we can see from this block diagram? Like FA0, like a FA1 is not waiting for FA0, FA2 is not waiting for FA1, FA3 is not waiting for FA2, like how it was waiting inside the ripple carry header, right? So we have removed that. Okay, so inside CSA, it will remove that chain. Okay, like in ripple carry adder, we had chain, right? Like it was waiting for the previous stage to calculate its carry, right? So here what we are doing, this full adders. Okay, full adders which have have particular operation on that set of bits will work simultaneously, like parallel operation. So that is why CSA is faster. Why faster? Because they have no carry dependency on other full adders. Okay, so how you are going to calculate this sum vector? Like we are getting here S3, S2, S1, S0, right? How you are going to calculate that? Okay, that we have formula. What is the formula? Like A XOR of B XOR of C. Okay, this is what the sum equation looks like. And for carry, A and B plus, plus means OR operation. B and C OR operation. A and gate C. Okay, so this is what we are going to write inside carry and sum equation. Okay, so for sum to achieve something, among these three inputs, only one input should be activated time, right? Then only your sum is going to generate. Okay, otherwise no sum will be generated, right? So for carry, based on this equation, if you calculate what is the bit of every inputs, then you will going to get the output, right? Because we are not going to discuss on these equations, because previously we have learned like how to solve this equation using truth table, right? So when is the carry generated? When can you say that carry will be generated? Look the inputs and outputs. You can see, right? We have three zeros, no carry is generated. Only one input as one, no carry generated. But here we have two input as one, then carry is generated, right? So to generate the carry, among three inputs, at least two inputs, should be one. Okay, so then only you are going to generate the carry. So this is what this equation is going to tell, like at least two inputs out of three inputs, that are A, B and C, two inputs should be active at a time, then only you are going to generate the carry. So next, to coming to a numerical example. Okay, so now we have A input as 4 bit, like that are 1010, B as 1100, C is equal to 0111. Okay, so what is the answer we are going to get? Base First we need to calculate, like put an adder for that particular bit, like A0, B0, C0, one adder, like that. For also for A2, B2, C2, A1, B1, C1, A3, B3, C3. First we need to calculate that, right? So see here, this is third bit, second bit, first bit, and zero bit of A, B, C. We have divided, written inside a table. And what will be the sum of these three bits? What I said, to sum, to generate a signal, only one input should be activated time. But here we have two inputs, right? So zero. For here also two input is activated time, so zero. Here also two input is activated time, so zero. And here we have only one input activated time, right? Then only your sum is going to generate. For carry, here we have two input activated time, one. Here also we have two input, one, two input, one. Here only one input, so it's not going to generate the carry. Okay, so what did you get your answer as? So for some, you would get, you got 0001, right? Like if you sum every bit that has been generated, you are going to get 0001, right? For carry, you got 1100, right? So before thinking about this line, just manually add this. Okay, so what the answer you are going to get? Like what is the decimal value of this binary value? A value will be 10, right? B means 12. C is nothing but 7, right? So eventually if you add everything, you're going to get 29, right? Answer is 29. So just using that, just add this. Okay, see here, you're going to add bit 0. What we have bit 0 here? 0001, right? So what is the answer you are going to get? Sum is 1, carry is 0. Okay, for bit 1, 101. What is the value you are going to get? Some answer is 10, right? Sum is 0, carry is 1. For bit 2, 011. What is the answer you are going to get? 10, right? You can ask 10, why 10? Because what is the answer if you add this equation, like 0 plus 1 plus 1? What is the answer you are going to get? 2, right? You are going to get 2 as answer here, and here also. Or you are going to write 2 in a binary form, 10, right? So that's why 10, I am telling us 10. Okay, so I will also, okay, I will, it will make you confused. I will just say 10. Okay, so you are going to get answer here as 10. That 0 will be sum and 1 will be carry, right? For the third bit, here also you have 110, then the answer will be 2, which is nothing but you are going to write in a binary form is 10. That 0 will be a sum and 1 is carry, right? So this is how you are going to generate everything. So what is the final sum vector you got? 0 0 0 1 and carry vector as 1 1 0 0, right? So before doing that, inside carry, we are going to shift into one numbers, okay? Like you are going to add 0 to last number. You can ask why we are shifting the carry to left, okay? So we are adding carry because there is something called as carry generated a bit I belongs to bit I plus 1, okay? So this is nothing but what we are used to do, like adding two numbers 1 1, right? What will you get the answer as 1 0, right? 2, you will get 2 and the answer. If you convert that into binary form, then you are going to get 1 0, right? So the always the carry is moving to left side, right? Inside that always moving to left side. Or you are just write this as 1 and 1. You will get 2 answer. If you are converting that to binary form, then you can write as 0 1 carry, right? Like you are shifting to 1, right? So that's why we need to shift, okay? So just remember this line: the carry generated a bit I belongs to I plus bit, okay? I plus 1, okay? It belongs to I plus 1. The carry generated by bit I belongs to I plus 1, right? Why I plus 1? Because you are shifting carry to a next value, right? I will show you later. I will show you notepad. Now is it screen visible? Okay, wait. Yeah, okay. Look, we were explaining this, right? So why are we shifting that carry to next side? Why? Because what happens if you are adding like 1 plus 1? What will happen if you add these two numbers? You will get answer as 2, right? So how you are going to write that 2? 1 0, right? In the binary form. Then this 0 will come under this 1 and your carry will be generated here, right? So it will be shifted to the left, right? So that's why you are going to get shift your carry also, because what I said, the carry generated by a bit I will always belongs to bit I plus 1, right? So seeing this, you can say this is as 0 bit, okay? This is the 1 1 you are seeing right here. 1 1. This is a 0 bit. This is a first bit, right? So where your carry is now going? Your carry is going from 0 bit to this bit 1, right? So that is what the meaning of the carry generated by a bit I always belongs to bit I plus 1. Okay, so that's why we are shifting to left side. Okay, so if you shift to left side means what will happen now? Your just look here. Now your carry is like this, right? If you shift means what will happen? One will come here, another one will come here, 0 0. Now you don't have any numbers to add here, right? So it will shift like this. So if you don't have any numbers means 0 will occur in that place. Okay, so this is how you are going to shift. So this is the final result that you are going to get after shifting the carry. After shifting the carry, then now you have sum of every bit. Okay, so until now your carry is stored. Okay, stored by every adders. Okay, so what will you do to now you get your every sum bit and carry bit? What you are going to do now? For for this carry and sum bit, you are going to add this. Okay, so you are going to add, this is what your carry bit is looks like, right? Then your sum bit will looks like this, right? 0001. Just because there is only 4 bit, so I written the final bit as 0. Okay, so just to like not to get confused, like why? Because it has 5 bits, we have only written 4 bits. Just to fill that place, we have used another 0. So this is what your final actual result will looks like. You need to add that. Okay, so before that I said CSA is not going to produce final result, right? Why? Because the job of CSA is only to produce sum bit and carry bit. Okay, now we add sum bit and carry bit, so we are going to use another adder. Okay, final adder which is going to add this sum bit and carry bit. Okay, so inside that final adder, okay, the adder which you are going to use is which can you can use three types of adder, like RC ripple carry adder, or CLA carry look adder, or Coxstone. Okay, Koggestone, and there are another two adders other than this Coxstone. Okay, so they are called as parallel adders. I will explain in next class. Okay, so just think we have some kind of adder called as Coxstone adder. Okay, so I'm just asking like one question: what happens if you use final RCA adder, final as a RCA adder? We can use any adder from these three adders. Okay, so what happens if you use RCA? Obviously the speed will is going to decreases. If you use CLA means the speed will improve, right? So based on like your requirement, you can use either RCA or CLA. Okay, so and Coxstone is nothing but like it's make even faster. Okay, so I will explain this adder in next class. So coming back to the complete CSA design, it look like this. Okay, first with three inputs, for every bits you are going to use adders, separate adders, and that adder is going to generate some bit and carry some vector and carry vector, and that is not the output of CSA block. Okay, for output of CSA block, you are going to only get sum vector and carry vector. But to get the final output, you need to use a final adder. Okay, so that adder will give you answer. Okay, some that will be 5 bit. Why 5 bit? Because you got carry as 5 bit, right? Carry vector as 5 bit. Okay, obviously then if you have one input as 5 bit, then you will get output as 5 bit only. Okay, so what is happening here? Like I said, in inside RCA and other adders, there will be like carry propagation delay, right? So inside CSA also we also have that delay, but compared to other adders, the delay will be less. Like what will be the delay? The delay is going to be, is of one full adder delay. Okay, there is only one full adder delay. Okay, in any CSA architecture design, there is always going to only be one full adder delay. Okay, so just remember that word. Why one only one full adder delay? Because where you are calculating your carry, you're calculating your carry inside this final adder, right? Why? Because you don't here inside this four full adders that you have inside used inside CSA, like for A0, A0, B0, C0, one adder, B A1, B1, C1, another adder, right? There you are not going to calculate the carry. You're just storing, saving the carry. But where you are adding your carry inside the final adder, right? So that time, only at that time you are going to get the delay. Okay, so compare like if you are think about RCA, your carry will be transferred to next adder, right? So there you are going to, depending upon your bits, your full adder delay will be determined, right? If you are using 4 bit, then it will be 4 full adder delay, right? So but here we have only one full adder delay. Okay, so just remember this, CSA is only going to produce one full adder delay. When it's going to produce that delay in final adder. Okay, so this is but nothing but delay analysis. Okay, like we already learned this delay, right? Like it will be have around 8 bit delay, 24 like that, like 8 gate delay, 24 gate delay. Like just remember this, take a screenshot of this delay analysis. Okay, so TG is nothing but one gate delay. Okay, that will be around typically around 0.1 to 0.3 ns. Okay, in 28 nanometer. If you are converting that into nanometer means 28. Okay, so this is what there will be delay of in every other adders. Okay, so just look the CSA and CLA. If you use CSA and CLA obviously the speed will be more than RCA, right? But inside, if you are using that inside a CSA, then the delay is almost negligible, right, compared to other delays. So just remember that this kind of delays is going to create inside that. Okay, so no one will ask like what will be the approximate delay that will be generated. Like if you are going to read a advanced concept like for denial analysis and other things, this will help you remember like what will be the delay created inside that particular. Okay, So this is just a like difference between CS and RCA. Okay. So inside RCA we have only two operands, whereas carry save header we have three operands. So output final sum directly was giving whether it has coming to carry save header, some vector, carry vector, like that where it was going. Just take a screenshot of this also, and just for study purpose learn these differences. Okay. So next, Verilog design. Okay. So like for I thought like how we are going to approach delays, right? So the task is create a Verilog design for carry save header and test bench, and give some test cases, and post take a screenshot of that and post in a WhatsApp group. Okay. So that's this will be the task for today's class. Okay. So why I'm telling you guys to do this, because like every time we should know how to write the Verilog code, right? So yeah, this is what I'm going to give you a task. Just to complete the task and post in the group. Okay. Like I hope everyone got a better understanding of carry save header concept. Okay. So that's it for this class, guys.